Okay, so at this stage in the game, my hope is that number one makes perfect sense because number one is really just what we've been doing every day up until this point in this new unit. So it was just a basic exponential growth situation. 3.5% growth becomes 1.035 as the change factor. Vertical intercept was 192 years worth of growth. So I'm not going to talk about that one much more because that one is strictly a review. I'm going to move on to number two because here's really where the newness of this week comes in. So, in this situation for number two, when you invest your money into a typical bank account, you're not going to get annual compound interest. For the most part, our bank investments typically compound every month. If you were to pull up your regular savings account right now, I'd bet you money, pun intended, I'd bet you money that on October 1st or whatever the first of the month was, there you're going to see the word dividend. And next to the word dividend, there's going to be some pennies. And that was essentially the interest that you earned that month. Most banks acquire interest each month. Are there other ones like quarterly and other things? Yes, there are. We'll talk about that, but most of it's monthly. So, how would that affect our exponential growth? Let's take a look at number two. So number two says many bank accounts invest monthly or quarterly, etc. So let's imagine that you had a $4,500 investment into a money market account. And what that brochure or flyer or whatever it is that they were showing you when you opened this account tells you that you're going to now earn what's called a nominal interest rate of 4%. But here's what it's going to say. It's going to say 4% compounded monthly. How much money do we have after 5 years? Okay, so when you set this up, first of all, your initial investment is obviously 4,500. So that's your vertical intercept, so to speak. And then I want you to think about this, and I'm going to purposefully write it like one small step at a time because I want you to see how all these pieces break down. So, first of all, if we're talking about a banking investment and not the stock market, as long as you put your money in there and then don't touch it, it will grow. It's not going to decrease. The stock market is viable, that could decrease. Volatile, not viable, volatile. The stock market is volatile, that could decrease. But a basic savings account, money market account, certificate of deposit account, these are all very safe investments that once you open them, they will increase. So for that reason, I know that my change factor is going to be a growth. So I'm going to say 1 plus. But now here's where the newness comes in. You're going to earn 4%. So a lot of times students are like, oh, plus 0.04. No. Hope you weren't using pen. No. Yes, it says you're going to earn 4%, but it says you're going to earn 4% compounded monthly. So what that ends up meaning is you do not get 4% every month. What they do is they take the advertised rate of 4%, so 0.04, and they spread it out amongst the calendar year. Spread it out, divided by the 12 months in a year. You will not get 4% every month. They're going to take the 4% and they're going to spread it out monthly. Now, when you first learn that, you're like, well, that sucks because I really wanted to get 4%. 4% divided by 12 is a really tiny number. Okay, I hear you. And yeah, it doesn't sound great, but here's how they make up for it. The number of times that you're going to see your account get updated in those 5 years is every single month for 5 years. So remember for granddad's investment, 92 years worth of time was just a power of 92. Well, in this case, 5 years of time is actually 12 times a year for 5 years. They're going to update your account every single month for 5 years. So you're going to see way more than five dividends in your account. You're going to see a total of 60. Now, where that 60 comes from is every single month, 12 times a year for 5 years. Can you see how that's going to be 60 right there? 60 compounds over the course of 5 years. And so that really large exponent is what makes up for this bummer of a feeling that they divided your interest rate by 12. These kind of work itself out almost. Like this gets really small, but now this gets really big, and it works itself out. So when you put this in Desmos, first of all, I want you to type it in all at once. We are not going to do this piece by piece. I'm going to literally type exactly what we had. I'm not going to simplify any of it. So 4,500. Can I zoom in at all? I can. 4,500. Oh, but now I can't see my thingy. Just kidding. Okay, times 1 plus the 0.04 divided by 12. So just type it all at once. And then raised to the 12 times 5. So that is how you would type that. And you can see that after 5 years, we're going to have $5,494.48, 5494.48. So 5494. What did I just say? Gosh darn it. 5494. Yes. 5494.78. Why can I not remember my numbers today? 48. Oh dear, 48. There we go. All right, so that's how much money you'd have if you invest this money into an account that compounds monthly. Well, now think about what would change if it was the exact same situation, but instead it's compounded quarterly. So would the $4,500 original investment be the same? Yes, it would. So you're still going to start with 4,500. Would the situation still be a growth? Yes. Would you still be earning 4%? Yes. Is it still going to get spread out over 12 months? No. They're now going to update your account quarterly. There are 4 quarters in a year, so you're going to get your account updated 4 times throughout the year. So they're going to take the interest rate and divide it amongst those 4 times. And then in the span of 5 years, are you still going to have 60 compounds if it's only compounded quarterly? No, it's now 4 times a year for those 5 years. That'd be a total of 20 compounds. So 4 times a year for a total of 5 years actually amounts to 20 times that they will update your account. So all that changes in that context is that since it's no longer monthly, now it's quarterly instead. These are now fours instead of 12s. And if we change that in Desmos, so instead of monthly, it is now quarterly. There we go. Notice you'll make just a little bit less money because the more compounds, the better. We know how exponential growth works. The higher the exponent, the larger the result. So in this case, it's a little bit less, but 54.90, 85. Now notice I'm not going to round the 85 to 86. In banking problems, we typically don't round at all because let's be real, the bank's not going to give you a single extra penny that they don't think you deserve. Isn't that annoying? So typically we just cut off the decimal. So 54.90, 85. 54.90, 54.90, 85 is how much that account would earn. Okay, so if you think about it, we could now have all sorts of different problems that are posed in the same manner, and they're all going to follow this structure. You're always going to have that initial investment. These will always be growth problems because, again, the banking industry is a safe investment. We are not talking stock market. You're going to have your interest rate that gets spread out based on what they tell you, monthly, quarterly, etc. And then up here, you still have those compounds for however many years we have the account for. So you can already feel how all of this wants to lend itself to a formula. And yes, it absolutely does lend itself to a formula. Here she is. Here's the formula. So, as we kind of saw in those previous examples, this is the formula that you can now have in your notes regarding these banking problems. You're only going to use these banking or this banking formula when you see compounding interest. This is only valid for compounding interest. But in these models, you always start with that initial investment. This is like your vertical intercept. But in the banking world, the vertical intercept is called your principal balance. So that's why they use the capital letter P. The initial amount is called the principal account. Then, like we said, it's always going to be a growth. So one plus, and then you've got your interest rate that gets spread out. So R is our interest rate in decimal form. Excuse me. And then that lowercase n is just however many compounds there are. If it's monthly, it'd be 12. If it's quarterly, it'd be 4, etc. And then the exponent is similar. You're going to have however many years go by. So variable t is however many years go by. But then how many times per year? Remember, if it's monthly, it was 12 times a year, quarterly, 4 times a year. So this same value down here gets reused up there based on how many compounds we're talking. Some of the most common compounding frequencies, just if you wanted to have these jotted down. So the most basic, I suppose, would be annual, just once a year. Semi-annual would be twice a year. We saw quarterly, which is 4 times a year. We saw monthly, which was 12 times a year. And the last one that you might see is daily. And for daily, we just assume that it's not a leap year and we just do 365. Now, certainly don't get me wrong, if it really was a leap year, these are all for your N values. Certainly if it was a leap year, you would get the extra day, just so you know. It would be 366 in the real world if it was a leap year. But for the sake of a math classroom, we just keep it at a typical 365 calendar year. So these are all the different values of N that you might come across. Semi-annual N is 2, quarterly N is 4, daily N is 365, and monthly N would be 12. Because again, these are the compounds per year that we're talking about. So you can have these written down if you want to, just as the most common values of N. Okay, so last thing on this front page, how long does it take for the investment with the conditions from problem 3, so that'd be this one, problem 3, to reach a value of 83.50? Okay, so how long does it take for me to have this much money in my account? So notice that's the ending value. That's how much I plan to have as my ending investment value, my final amount after I've let my money sit in there and grow. So when you're thinking about what this problem's trying to ask of you, 8350 is wanting to be like that output, that final amount. Now we're still investing. This is the conditions from problem 3. So we're still investing 4,500. It's still a growth context, so 1 plus. With the conditions from problem 3, we'd have that 4% interest rate compounded quarterly. But now here's where you want to be careful. Is it going to take 5 years? No, it's going to take more than that. How much more? I don't know. But I don't know how many years it takes. All I know is that it is still quarterly. So the 4 is still there, but I do not know the unit of time. That's a lowercase t. That's my variable. I don't know how long it takes. Now, this is that perfect scenario. We did this last week of I now need to solve this equation, right? Like I need to find out how long does it take. Well, we're not learning how to solve this by hand in this class. So the only option we have is to hop into Desmos. So in a second, I'm going to put all of this into line 1 of Desmos. And then in line 2, I'm going to tell Desmos that what I would like is a desired output value of 8350. So this is what's going to go in Desmos. So let's see. All right. What did we say? We said that all this was going to be the same, except now I do not know how long it takes. So I'm just going to make it input variable X for the sake of Desmos. I could probably use T. Sometimes Desmos is fine with the letter T, but just to be safe, time is my input variable. So for the sake of Desmos, I'm just going to say X. And then for line 2 in Desmos, we're here to ask Desmos essentially, when will the output variable reach 8350? So letter Y for output and then 8350, 8350, there we go, is the desired output. So right now I can't see anything on my graph, at least not very well. And we could try zooming, but guys, we talked about this last week. If you try just to zoom, you're going to end up in what I jokingly call window hell. You don't want to get lost in window hell. Let's just try to be smart about this. I'm going to go into my little wrench up here in the top right hand corner. The x axis in this problem, remember x was t, time. X is time. How many years is it going to take? Well, I don't know, and neither do you. But I think we can hopefully assume it's within our lifetime. I mean, I hope it doesn't take 10,000 years. Otherwise, this was a crappy investment on my part. So, for the sake of the x-axis, I have time zero, meaning like when the account first opened. And then if we assume that it happens in our lifetime, I'm going to say maybe 50 years on the x-axis. So 0 to 50 would be a reasonable amount of time, I hope. And then the y-axis, okay, we're talking about our investment. Remember we put $4,500 into this account? So at the very minimum, we're going to have that much money in there. So I might choose maybe 4,000 as the low end of my y-axis. And then on the upper end of my y-axis, well, remember, we're here to solve for 8350. So I already know that I want a y value to be 8350. So I might put like 9,000 just to kind of give myself some wiggle room. You can put 9,000, 10,000, just something big enough to see 8350. I'm going to put 9,000. And now if I tap my graph, there we go. I can like zoom a little bit now and I can like see much more clearly when I zoom that this right there, that is how long it will take for my black exponential growth curve to hit a Y value of 8350. So 15.53 is the answer that we get. So T equals 15.53. And remember, in these problems, T is indeed a unit of years. So this is what we get for the answer to this. 15.5 years until our investment reaches that dollar amount. Okay, we will come back in a minute and talk about the backside.